Hello students, welcome to Allen Digital. Today we are going to study about the most famous reaction of alcohols named as dehydration of alcohols. By the name itself, it suggests dehydration. D means removal, hydration means water. So you will be having a loss of water in that particular reaction. So let us start. What is that reaction? What are the substrates? Under what catalyst or under what temperature we are going to do that reaction? All that phenomena we are going to study now. So let us start with the reaction, students. Dehydration, or mostly called as acidic dehydration of alcohol. That means you are going to do this dehydration in the acid medium. You are going to do this dehydration in the acid medium. So acidic dehydration of alcohol is an example of elimination reaction. What is it, students? It is an elimination reaction because loss of water can be seen. So elimination reactions always includes cleavage of bonds. So that bond cleavage requires more energy. That is why they have to be done at high temperature. They have to be done at high temperature. So the reagents, what are the reagents used? We can use the reagents like concentrated H2SO4 and high temperature has to be maintained. Concentrated H3PO4, high temperature required for sure. H plus in the presence of high temperature. What is going to happen in this reaction? We take an alcohol CH3CH2OH. We are treating this alcohol with a concentrated H2SO4 at a high temperature like 170 degrees Celsius. This temperature condition is important. And this alcohol, upon treatment with acid at high temperatures, undergoes elimination to form an alkene and loss of water can be seen. So what is the note of this reaction? Dehydration of alcohols is favored at high temperature. So we have said that the alcohols are undergoing elimination to form alkenes in the acid medium at a high temperature. But the most important question is how this change is happening. Yes or no? That is the most important part of understanding any organic reaction. So that question how can be easily explained if we just look at the mechanistic approach. So let us start with the reaction, students. I have taken an alcohol like CH3C, CH3, CH3OH, a tertiary alcohol I have considered. What is going to happen in the course of reaction we will analyze first. We are treating this alcohol with concentrated H2SO4. What is H2SO4? H2SO4 gives, H2SO4 will be giving H plus and HSO4 minus. H2SO4 is an acid, means HSO4 minus will be the conjugate base. Look at the mechanistic approach. H2SO4 dissociates to give H plus and HSO4 minus. H2SO4 is your acid. HSO4 minus is the conjugate base. Conjugate base. Right? We have an alcohol. In the alcohol, we have a carbon-oxygen bond and oxygen-hydrogen bond. And on oxygen, we have two lone pairs of electrons. From the H2SO4, we get the H plus ion. So this H plus ions can be attacked by the lone pair of electrons on oxygen. Yes or no? The lone pair of electrons on oxygen, they can attack the H plus. As soon as they attack, what you are going to generate? You are going to form a new OH bond. You are going to form a new OH bond. Look carefully. Whenever H2SO4 is giving up H plus ion and the H plus ion is attacked by the lone pair of electrons on oxygen, the new OH bond is formed. What happened to the positive charge of hydrogen now? The positive charge of hydrogen has to be nullified. Why? Because it has gained the electron density. What happened to the oxygen? Earlier oxygen itself has the lone pair. Now the lone pair of electrons on oxygen were shared between oxygen and hydrogen. So electron density on oxygen has been decreased. So oxygen should be having a positive charge. Look at this statement now. Carbon connected to oxygen, oxygen has two OH bonds. It is nothing but your protonation of alcohol. Alcohol is protonated in the step 1. In the step 2, what happens? The positive charge on oxygen is not stable. Why? Because oxygen is more electronegative in nature. The electronegative atom attract the shared electron density. So electron density wants to move towards oxygen now. Which electron density? The electron density in the CO bond is moving towards oxygen. So what happens to the carbon? It has to develop positive charge. But will it happen at a fastly or will it happen at a slow rate? If you look at this particular cleavage, the carbon-oxygen bond has to be lost and we are getting water. Because the bond is cleaved, the reaction will happen in this particular path in a slow way. The slowest step of the reaction is always the rate determining step, that is your RDS. Rate determining step, that is your RDS. We obtain a carbocation. Step 1 is the protonation of alcohol. Step 2, loss of water to form a carbocation. Once the carbocation is formed, once you generate a carbocation, the carbocation can undergo rearrangements like 1, 2 hydride shift, 1, 2 methyl shift or ethyl shifts. Different rearrangements are possible for carbocation to get a more stable carbocation. So those rearrangements you have to do and you have to generate the most stable carbocation. The most stable carbocation will now undergo elimination, leading to the formation of alkene. How this elimination will happen? Because we have HSO4 minus, right, which is your conjugate base. This conjugate base will try to pick up the proton and the CH electron density comes into, leading to the formation of alkene. The conjugate gas can pick up proton from different carbons. So you have to generate an alkene which will be most substituted. Like shades of alkene has to be given as a major product with some exceptions. That is what the mechanistic approach of your dehydration of alcohol. If you summarize, step 1, protonation of alcohol, OH converted to OH2 plus. Step 2, remove the water, which is a rate determining step. So dehydration happened here. Whatever the carbocation obtained, that will undergo rearrangements. In the final step, elimination happened. That means you are getting an alkene. So what is the summary of this particular dehydration reaction? Remove OH and from carbocation, check out rearrangements in carbocation and finally form the double bond. Understood, students? So this is the mechanism of your dehydration of alcohol. Now let us take some examples and also understand where the dehydration is going to be greater. First, if you take down few notes, dehydration of alcohol is catalyzed by an acid. It is an acid catalyzed reaction. That means acid will increase the rate of the reaction. Why? Because in the step 1, we have seen the lone pair of electrons on oxygen, they attack the proton. Yes or no? So it is acid catalyzed. Carbocation is the intermediate form. So rearrangements are possible. Rearrangements of carbocation are possible. Rate of dehydration, that means I have given different sets of alcohols to you and asked you to figure out which alcohol will undergo dehydration fastly. Then you have to just look at stability of carbocation. So which alcohol is giving most stable carbocation, that will undergo dehydration at a faster rate. So if you look at the third point, can you apply the third point to these three sets of alcohols? We have a tertiary alcohol. This is your secondary alcohol. This is your primary alcohol. The tertiary alcohol will give tertiary carbocation. Yes or no? Because OH2 plus if it is lost, we get a positive charge here, which is a tertiary carbocation. Same thing you do with the secondary, you get a secondary carbocation. Same thing you do with the primary, you get a primary carbocation. So which is carbocation is more stable? We all know that tertiary carbocation is more stable than secondary, than primary. Why? Because tertiary carbocation has more number of hyperconjugative structures when compared to secondary, and secondary has more number of hyperconjugative structures when compared to primary. So this alcohol will undergo dehydration greatly, then the secondary alcohol, and then the least is going to be primary alcohol, right? So dehydration of alcohols is acid catalyzed. Carbocation is intermediate is formed. Carbocation intermediate is formed. So rearrangements are possible. Rate of dehydration is directly proportional to stability of carbocations. Let us take an example. So we have an alcohol given to you. What I can do first? The alcohol, whatever they have given to me, I can treat with H+. H+ is obtained from H3PO4 or H2SO4. What I am going to generate? Lone pair of electrons and oxygen attacking the H+. I am going to generate protonated alcohol, that is OH2 plus is obtained. Now rate determining step, what I will do? I will simply remove water and generate a carbocation, which is your most stable carbocation in this case, because there is no possibility of tertiary carbocations. Now I have to do the elimination. So to do the elimination, if I look at the hydrogens, so the HSO4 minus, or here we have H2PO4 minus, the conjugate base, that can pick up this proton, and the CH electron density can come into, leading to the formation of this alkene. Since if the other hydrogen is also picked up, we are getting the same alkene, so that is going to be a major product. So you can simply say, so the carbocation is formed and it undergone elimination to form an alkene, which is nothing but your major product. This is a simple reaction, right students? Let us try to understand different other example. So we have given a 5-member ring connected with a CHOH and CH3. What will happen in the first stage? We have the 5-member ring. The OH can be converted to OH2 plus. Yes or no? If I treat with H plus, what will happen once OH2 plus is formed? Loss of water. It will be forming a 5-member ring, and loss of water obtained. We get a carbocation like this. Whenever we get a carbocation like this, it is a 2-degree carbocation. You can generate 3-degree carbocation, but there is a possibility of expanding the ring. So ring expansion is given the most priority. For expanding the ring, always preferably give numbering. So I give you numbering 1, 2, 3, 4, 5 and 6. These are not IUPAC numbers, students. The numbering is just given to locate the substituents after you have written the 6-member ring. So I can cleave the 2,6 bond or 2,3 bond. Ring expansion occurs fastly, so you can cleave any bond. So 2,3 bond you can cleave. So how you can write the 6-member ring? I can simply write the 6-member ring. Earlier I have a bond between 2, 3. Now I am generating a bond between 1 and 3. So let us say this is your first carbon. 1 and 3 is now having a bond. 1 and 2 bond are not disturbed. 1, 2, 2, 6, 6 to 5, 5 to 4, 4 to 3, 3 to 1. Look at which carbon has seen the net loss in electron density. The electrons are present between second and third carbon earlier. Now they are shared between first and third. So is it the second carbon which seen the net loss in electron density or not? So the second carbon will be having a positive charge now, because it has seen the net loss in electron density. First carbon gained the electron density, so positive charge should be nullified. Third carbon, no loss or no gain, so no charge. So first carbon has a methyl substituent, so I can keep that substituent as it is. Yes or no? I can keep that substituent as it is. Now what I can do, students? Now what I can do? This is a carbocation which is 2-degree carbocation. I can convert this 2-degree carbocation to a 3-degree carbocation or not? Yes or no? Is there a possibility? Because if I get a positive charge on the first carbon, that would be a 3-degree carbocation. So to generate a positive charge on first carbon, on the first carbon I also have a hydrogen. So I can do a rearrangement, that is 1, 2 hydride shift. What I can do? 1, 2 hydride shift I can do. If I done the 1, 2 hydride shift, I am going to generate a carbocation like this. And this carbocation, which is the most stable carbocation or tertiary carbocation, will now undergo elimination. It will now undergo elimination to give the most stable alkene or the most substituted alkene, which is going to be your shades of product, which is nothing but this alkene. So this is going to be your major product, because I cannot remove hydrogen from that methyl. If I do so, I will get double bond outside. I can remove hydrogen from this carbon, that is 6th one, or from the 3rd one, generating same type of products. So this reaction actually involves ring expansion, rearrangements, and generating the major product. That is why it is a best example to understand dehydration of alcohols. In this video, we have seen how dehydration of alcohols will be done. In the dehydration of alcohols, what are the reagents used and what is the catalyst used and what type of products are obtained. So if you try to summarize the things whatever we have studied, we have taken an alcohol, treated that alcohol with an acid. From the acid, whatever the H plus ions are we obtain, that is reacting with the OH group from alcohol to form a protonated alcohol. That protonated alcohol will undergo loss of water to form a carbocation. Carbocation, whenever it is obtained, the rearrangements or ring expansions can occur. Ultimately, we will be producing the most stable carbocation, which will be undergoing elimination to form shades of alkene. That means the alcohols are converted to alkenes in the presence of acid catalyst, and the reaction has to be done at high temperature. If not, substitution can also occur. And we have also seen which alcohols will be undergoing with a greater rate for these dehydration reactions. And finally, we have seen 2 examples involving dehydration of alcohols. Fine students, thank you all.